Venus is our closest neighbor. Mercury orbits even closer to the Sun. Mars is the planet everyone talks about visiting. And then there are the giants: Jupiter, Saturn, Uranus, Neptune. The travel times to these worlds are not what you think. Because here's what nobody tells you. Proximity doesn't determine difficulty. The closest planet isn't the quickest to reach. The farthest isn't always the slowest. And the planets we can actually visit require commitments most people don't understand. The moment you leave Earth's orbit, distance stops being measured in kilometers. It starts being measured in survival. The real numbers for each planet will surprise you, because the answer is not what you expect. And by the time we reach the outer planets, you will understand why most of the solar system is not just difficult to reach, it is biologically unreachable. Every spacecraft that has ever left Earth carries a problem it cannot escape: mass. Everything you need to survive adds weight: food, water, oxygen, radiation shielding, spare parts, computers, propulsion fuel. And every kilogram of that mass requires fuel to accelerate. But fuel has mass too, so you need more fuel to move the fuel. And that additional fuel adds more mass, which requires even more fuel to move. It compounds. Before you even fire the engines, the spacecraft is trapped in a recursive equation where every solution creates a heavier problem. So space agencies do what they must. They optimize for fuel efficiency instead of speed. They use something called a Hohmann transfer orbit, fire the engines once to leave Earth, coast along an elliptical arc, and fire again at the destination to slow down. It is mathematically elegant and brutally slow, because the Hohmann transfer does not care about your schedule. It does not care that faster travel would reduce radiation exposure or psychological strain or the risk of equipment failure during transit. It cares about one thing: using the least amount of fuel possible. And that means accepting whatever travel time the physics demands. For the inner planets, that means months. For the outer planets, that means years. And there is no way around it unless you are willing to carry exponentially more fuel, which makes the spacecraft so heavy that no rocket we have ever built could lift it off the ground. You cannot engineer your way out of this. You can only accept it. Which brings us to the planets themselves. And the first one is not what you expect. Venus is Earth's closest planetary neighbor. At its nearest approach, only 38 million kilometers separate us. That is closer than any other planet will ever get, which makes it sound easy. It is not. A mission to Venus takes 3 to 5 months, 90 to 150 days of transit time for a planet that sometimes sits closer to us than Mars ever will. The reason is velocity. Venus orbits the Sun faster than Earth, does 126,000 kilometers per hour compared to our 108,000 kilometers per hour. To reach it, a spacecraft does not fly outward. It falls inward toward the Sun, shedding velocity, timing the descent so Venus intercepts the ship at exactly the right moment. That inward fall is what consumes time. You are not traveling to Venus. You are falling toward the Sun and hoping Venus catches you when you arrive. Miss the timing by even a small margin, and the spacecraft sails past into a useless orbit, or worse, continues falling sunward into a trajectory it cannot escape. The launch window opens every 19 months. Miss it, and you wait 1.5 years for the planets to realign. No exceptions, no shortcuts. Venus is the closest planet, and it still takes months to reach, and only when the solar system permits it. But Venus is not the worst case. That distinction belongs to a planet even closer to the Sun. Mercury orbits just 58 million kilometers from the Sun. From Earth, that puts it between 77 to 222 million kilometers away, closer than Mars at its nearest, closer than Venus at its farthest, and completely inaccessible by any direct route. Because Mercury is not just close to the Sun, it is fast, faster than any other planet. It screams around the Sun at 170,000 kilometers per hour, and to reach it, a spacecraft has to lose an enormous amount of velocity to avoid simply flying past at interplanetary speed. Slowing down in space is expensive. It requires fuel, more fuel than speeding up, because when you accelerate, you are adding energy. When you decelerate, you are throwing energy away, burning fuel just to go slower. And carrying enough fuel to brake that hard makes the spacecraft so heavy that lifting it off Earth becomes the bottleneck. So missions to Mercury do not fly directly. They use gravity assists, multiple gravity assists. They fly past Venus, sometimes multiple times, using its gravity to bend the trajectory and bleed off speed without burning fuel. They fly past Mercury itself, using its own gravity to slow down incrementally across several passes before finally settling into orbit. NASA's Messenger probe took 6.5 years to reach Mercury. Bepi Colombo, launched in 2018, will take 7 years. 7 years and 9 planetary flybys, just to slow down enough to stop at a planet that is sometimes closer to Earth than Mars. Mercury is not far, but the velocity required to reach it turns proximity into a disadvantage. Distance does not determine difficulty. Physics does. And Mercury proves that being close is not the same as being reachable. But there is one planet we can reach. One destination where the timeline compresses just enough to make a crewed mission theoretically survivable. And even that mission requires a level of commitment most people do not fully understand. Mars sits between 55 to 401 million kilometers from Earth. Every 26 months, the two planets align in a configuration that opens a launch window. During that window, a spacecraft using a Hohmann transfer takes 6 to 9 months to reach Mars. One way, that sounds manageable. 6 to 9 months is long, but survivable. Astronauts have spent longer than that on the International Space Station. But a Mars mission is not the International Space Station, because the moment you arrive at Mars, a new problem begins. You cannot leave, not immediately, not for months. The return trajectory does not exist yet. Earth and Mars have moved. The fuel-efficient path home will not reappear until the planets realign, which takes approximately 500 days, a year and a half. So the crew waits on the Martian surface, exposed to radiation levels 40 times higher than Earth, breathing recycled air, eating pre-packaged food that has been sitting in storage for over a year, relying on equipment that has already survived a 6-month journey through space and a high-speed atmospheric entry, and now must function flawlessly on a planet with dust storms that can cover the entire globe for months. Every system becomes critical. The habitat seals that keep the thin Martian atmosphere out, the life support processes that scrub carbon dioxide from the air, the water recyclers that reclaim every drop of moisture, the power generators that keep everything running, the communication arrays that maintain the link to Earth. A single catastrophic failure in any of these during that 500-day wait creates a survival crisis with no immediate solution, and the psychological weight compounds with every passing week. You are standing on another planet, looking up at Earth in the night sky, a pale blue dot barely visible among the stars. Everyone you have ever known is on that distant point of light. Your family, your friends, the entire human civilization. And you cannot go home. Not yet. Physics will not allow it. You are trapped by orbital mechanics, waiting for a window that opens on a schedule you cannot control or accelerate. The isolation is absolute in a way that low Earth orbit never is. The International Space Station orbits 400 kilometers above Earth. Mars, at its closest, is 55 million kilometers away. Communication signals take between 3 and 22 minutes to cross that gap one way, depending on where both planets are in their orbits. Every conversation with mission control becomes an exchange of recorded messages separated by minutes of silence. If an emergency occurs, there is no real-time guidance, no immediate expertise. The crew solves it with whatever knowledge they have and whatever equipment they brought. Mission control sends advice, but it arrives minutes after the problem is reported. By the time the response reaches Mars, the crisis may already be over, one way or another. And if something breaks during that 500-day wait, if the habitat fails, if the life support malfunctions, if the return vehicle is damaged, there is no resupply mission, no rescue. The next launch window from Earth is 26 months away, and even if a rescue ship launched immediately, it would arrive 2.5 years later. By then, the crew would be long dead. So they wait and hope nothing critical fails. And when the return window finally opens, they launch and spend another 6 to 9 months in transit back to Earth. Total mission duration, 2.5 to 3 years. That is the minimum. That is the absolute best-case scenario where nothing goes wrong, every system functions perfectly, and the crew remains healthy enough to survive 900 days of radiation exposure, bone loss, muscle atrophy, and psychological isolation. Mars is the only planet in the solar system where a crewed mission is even remotely feasible, and it requires a 3-year commitment where turning back is not an option, where rescue is impossible, and where survival depends entirely on whether the equipment you brought continues working for the entire duration. Mars is doable. Barely. But beyond Mars, the constraints do not just get harder, they become unsurvivable. Jupiter sits 588 to 968 million kilometers from Earth. It is the first of the gas giants, and it is where the timeline stops being a challenge and starts being a sentence. The fastest mission to Jupiter was New Horizons' 13 months. But New Horizons did not slow down. It was a flyby, screaming past at over 48,000 kilometers per hour on its way to Pluto. No braking, no orbit. Just a snapshot and gone. For a mission that actually stops at Jupiter, the travel time stretches. Galileo took 6 years, Juno took 5. Both used multiple gravity assists, and both still required half a decade. For a crewed mission, the math becomes brutal. 2 to 3 years one way, 4 to 6 years round trip, 6 years in a metal tube with no resupply, no repair missions, no possibility of rescue if something fails. 6 years of radiation exposure far beyond anything the International Space Station experiences. 6 years of bone loss, muscle atrophy, vision degradation, immune system collapse. No human has ever spent 6 consecutive years in space. The longest single mission on record is 437 days, and that was in low Earth orbit with the option to evacuate. A Jupiter mission has no evacuation option. You leave and for 6 years, you are alone. If a critical system fails, you solve it with whatever you brought. If you cannot solve it, you die. And Earth will not know for tens of minutes, because even light takes that long to cross the distance. This is not a mission anymore. It is a commitment measured in years, where the human body itself becomes the weak point. Not the engines, not the fuel, biology. And Jupiter is still within the realm of theoretical possibility. The next planet is not. Saturn is twice as far as Jupiter, 1.2 to 1.7 billion kilometers from Earth, and the distance creates a problem that compounds faster than any engineering solution can fix. Cassini took nearly 7 years to reach Saturn, 7 years one way. For a crewed mission, that becomes 12 to 16 years round trip. 16 years. Think about what that means for life support alone. Food for 16 years. Water for 16 years. Oxygen. Spare parts. Medical supplies. Radiation shielding thick enough to protect the crew from over a decade of accumulated exposure. Every kilogram of supplies adds mass, and mass requires fuel to accelerate. But fuel has mass too. So you need more fuel to move the fuel, and more fuel to move that fuel. The equation spirals. Within a few iterations, the spacecraft weighs more than any rocket we have ever built can lift off the ground. And that is before you account for the habitat structure, the propulsion system, the power generation, the computers. You cannot carry enough to survive the trip. Not with chemical rockets. The mass required exceeds the payload capacity by orders of magnitude. And even if you could somehow launch it, the human body would not survive. 16 years in microgravity would cause bone density loss so severe that the crew would likely be unable to walk upon return. Muscle atrophy, immune system degradation, radiation damage accumulates in every cell. They would arrive at Saturn physically incapable of performing the mission, and they would return to Earth, if they returned at all, as physiological wreckage. Saturn is not just far, it is too far for the biology we have and the propulsion we can build, and it is still not the edge of the solar system. Beyond Saturn, the timeline stops being measured in years and starts being measured in decades. Uranus sits 2.6 to 3.15 billion kilometers from Earth. Neptune is 4.3 to 4.7 billion kilometers out. Both are so distant that only one probe has ever visited them. Voyager 2, 9 years to Uranus, 12 to Neptune. One way, for a crewed mission, double that, then double it again for the return. 20 to 25 years for Uranus, 25 to 30 years for Neptune. A human child born at launch would be an adult by the time the ship returned. The entire political administration that approved the mission would be gone. The engineers who designed the spacecraft would be retired or dead. The civilization that funded it would have changed in ways impossible to predict. And the crew would not be the same people who left. Not psychologically, not physically. A 30-year mission is not a trip. It is a lifetime commitment. You do not visit Neptune. You spend your entire adult life traveling to it and back. No training program prepares you for that. No psychological screening accounts for 3 decades of isolation. No medical protocol exists for reversing the cumulative damage of 30 years in microgravity and radiation. These are not missions in any meaningful sense. They are multi-generational commitments disguised as exploration, and no space agency, no government, no budget cycle operates on timelines that long. Uranus and Neptune are not on the roadmap. They are not in the planning documents. They are not part of the conversation about crewed spaceflight. They are simply too far for human biology, too expensive for human budgets, and too slow for human civilization to sustain interest across the decades required to complete the mission. The outer solar system belongs to robots, and it will for the foreseeable future. Because the problem is not technology, it is time. So here are the real numbers. Venus, 3 to 5 months, close enough to reach, but only when the solar system allows it. Mercury, 6 to 7 years, closer than Mars, but velocity makes it nearly inaccessible. Mars, 6 to 9 months outbound, 500 days waiting on the surface. 6 to 9 months back, 2.5 to 3 years total, the only crewed destination that is even remotely possible. And even that pushes human biology to its limits. Jupiter, 4 to 6 years round trip, theoretically possible, biologically unsurvivable. Saturn, 12 to 16 years, the mass required to keep a crew alive exceeds what any rocket can lift. Uranus, 20 to 25 years. Neptune, 25 to 30 years. Not missions, generational commitments. The problem was never the rockets. We built rockets powerful enough to leave Earth. We sent robots to every planet in the solar system. We proved that reaching these places is physically possible. But reaching them with people on board is a different problem. And the answer to that problem is not bigger engines or more fuel or better navigation. The answer is time and biology and the unavoidable reality that human bodies were not designed for the durations that interplanetary space travel demands. Every planet beyond Mars requires more time than the human body can endure in microgravity and radiation, more life support than any spacecraft can carry, more fuel than any rocket can launch. The constraints do not ease as technology improves, they compound. Every solution adds mass. Every kilogram of mass requires more fuel. Every year of travel time increases the biological damage, and eventually the mission becomes physically impossible, not because we lack the engineering, but because the physics and biology do not align. We like to imagine the solar system as humanity's future, a neighborhood waiting to be explored. But the deeper truth is harder to accept. Space does not become more hospitable as you move outward. It becomes less forgiving, slower, more isolating, more irreversible. And the distance between planets is not measured by the power of our rockets or the sophistication of our technology. It is measured by how long a human body can remain alive away from Earth. Right now, that measurement gives us one viable destination: Mars. Barely. Everything else is either too fast to catch, too far to survive, or too expensive to justify. That is not pessimism. That is physics. And physics does not negotiate.